Okay, now, so change of variables. Is this the whole entire
Yeah, this
course right here?
Yeah, this is the entire course that we're going to basically cover you. This is just one theorem. It's a claim about space that I'm going to try to explain to you in complete detail of how to prove it, what it means, what it's saying about the universe.
Okay.
And it's a very profound statement about
How do you pronounce this?
Diffeomorphism.
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 Okay. That sounds really intriguing.
Yeah. So we need to talk about what functions are first.
Okay.
So this is a type of function. What is so this is basically a function that's very nice, that has some special properties, okay? And those special properties make it a C1 diffeomorphism. But let's first understand what a function is. So G from omega into Rn is a function. Yes, so that's the first thing that we need to talk about, right? Before we even go here, let's take one step back and discuss omega. It's what's called an open subset of Rn. So omega, being a subset of Rn, this means it's a collection of points of Rn, basically. So omega, Rn is a set of points where it's like all of n-dimensional space, has all the points in n-dimensional space. Yes. So omega is just some of those points.
Oh.
So for example, in 3 dimensions,
some of them, are you saying as in like, have, like not all, okay.
Yeah, so like for example, I could choose the sphere in R3.
Yes.
And the sphere is just a collection of points. A collection of points in 3 dimensions. It's not all of the points. It's a specific subset of those points.
And that would be omega? The sphere.
That is omega. It's an example of what omega could be, but omega could be any subset. Any subset except for it has to be open. Now being open means that every point in omega, I can find if I zoom in close enough, I can find a sphere completely that surrounds that point that's completely in omega. Okay, so let me explain that. So basically, this is an open set. So basically, what this means is that let's just look at the plane now. Let's look at R2. So this means that omega could be something really weird, and it doesn't have to be connected like this. It could look something like this, even something very weird.
Yeah.
But the idea is that omega is actually the inside of these drawings that I've drawn here. It's not
It's not the actual.
Yeah.
Okay.
Yeah. Here, just stand like closer to the board so that everyone can see the board here. Okay. So basically, the idea is that every point in omega, this is a point in omega. If I zoom in close enough, there is a sphere, basically, that is fully in omega, that surrounds the point. So for example, this boundary point is not in omega, right?
Okay.
But if I go really close to the boundary, let's say here, it is in omega because I can find a small enough ball such that that ball is also in omega.
Okay.
Yeah? Yeah. So basically, that's the property of being open. So it's not like, if you take a piece of Play-Doh, for example, and it doesn't have any regions that are like perfectly flat or like don't have any, it doesn't contain its boundary, basically. Anything it's not going to contain any points on its boundary.
Okay.
Right?
Yeah.
Okay. And basically this allows us to understand, like every point is not isolated from its neighbors. Every point has a neighborhood of points that surround it, right? And that's important because in calculus we want to understand local behavior. So we want every point, we want to be able to look nearby that point and still make arguments. So basically, all of my arguments about this specific point, I actually want to make them about everything in its neighborhood. for example, if I was, ascribing to every point of omega, let's say I ascribed a color, then I would want this color, if I ascribed this to be green, then I would want every color around this point to be pretty close to green. I don't want the colors changing in a crazy way.
Okay.
That's a notion of a continuous function. Okay, so this explains what an open set is. Are we good to go on from an open set?
Yes.
Okay, so now let's talk about a function of this region here.
Okay.
This is our omega here. And now I want to talk about a function. So what a function does is every point, let's look at just a function from omega to Rn. So here's omega. And the idea is that a function takes an input and gives you an output. Okay?
Okay.
So in this case, the input is some point in omega, let's say p. And since omega is an R2, this point we can describe it in coordinates as x comma y.
Yeah.
Right?
Yes.
Then this mapping G will take the point x comma y and send it to some real number.
Okay.
Send it to...
Is G the point or the map?
G is the map. So G is an assignment. To every point I send you a real number. Okay? So, and we call this real number G of x, y. You don't know what it could be anything, right? So the idea is like every point I'm gonna assign it a number. Okay? And you could think of this as essentially a surface. So as is like if I draw omega now flat here, trying to draw omega flat on the kind of coming out of the board, and then if we assign every point in omega, we assign a height, then we end up with a surface, right? And the heights of this surface are exactly, this height is the output of the function.
Yeah.
Okay? Does that make sense?
Yeah. Okay.
So functions basically take points in omega and assign them values. So we can think of this as like a topological map. So I really think that we should think of like omega as, let's say, a map, and then if I assign every point in omega a height, it's like a topographical map. So have you seen topographical maps before?
I don't believe so.
Okay. Well then, that's fine. Then
I've seen the maps you created on the phone from the apps, but I don't know.
Yeah. So the idea of a topographical map is that it's kind of mapping elevation. So if you're going hiking, for example, the mountains, you want to be able to tell the different elevation heights.
Yeah.
Okay. And the idea is that, let's say that this surface has a height. Let's say this is the altitude of, let's say, 5,000 feet here.
Okay.
And I'm trying to create a map of some mountain. Then I need to understand, okay, the level, I have a map, a two-dimensional map, I need to understand the set of points with this height, okay? And that's going to be this constant elevation line. Okay? And these lines of constant elevation are important for you to understand because you're just looking at this map here and you can read off from this map the graph of the function, basically. And the function in this case is the elevation function. So the elevation function takes in the physical location on the plane and spits out a number, which is the elevation. Okay? So any function is going to take in a point in this plane and give you a number. It could be representing anything in real life, basically, any surface. But we could also have, so yeah. Do you have any questions about that? Okay.
That's good.
So I want to kind of help you understand what it means for it to be a C1 diffeomorphism. Okay, so the first thing you need to understand is that it's actually a continuous function. Okay, so first of all, omega in general is like an n-dimensional in Rn, and then this function is actually outputting. It's a collection of several pieces of data, namely, it's outputting n numbers. Okay. X1 to X2. So here's the idea, is that now, instead of just sending a function to the real numbers, okay, so instead of just our codomain being the real numbers, it's now Rn. So what this means is that let's look at R3, okay? And let's suppose that omega is on R3. Mm-hmm. So it's some subset of R3, maybe it's this kind of crazy looking subset of R3, okay? Mm-hmm. Now every point at omega now, and remember, this kind of looks like a shell, but omega is the inside. Is the inside of the shell. Everything in the inside. Yes. Okay, so every point in omega is going to get sent by our function g. A function g is just a map which sends points to different points, okay? And this is going to send the output not to a single number, like a height, but to now a number in Rn. So in this case, let's say it's R3, it gets sent to a different point of R3. So, we're basically morphing the surface. Or not the surface, but the thing enclosed by the surface, okay? So, does that make sense? So basically every point in here is getting sent to a point in here, okay? Now, so now, we want to understand what this C1 diffeomorphism means, okay? So it's sending omega to Rn. Mm-hmm. The C1 diffeomorphism means that if I look at a small ball around my point, right? Mm-hmm. And remember, we can always look at a small sphere or a small ball around the point because it's open. Okay? If I look at a small ball around this point, then the mapping G is going to map this to a small set. It's not going to be a ball anymore. It could be some weird looking thing, right? Mm-hmm. But it'll still map it to a small set. Okay. Right? Yeah. And that's the key, is that actually values that are nearby this point mm-hmm. get sent to values that are nearby in the image of the map. Okay. So in that way, it's not tearing apart the Play-Doh. If you think of this as like Play-Doh, it's not tearing apart the Play-Doh anywhere. And as long as pieces are close by to start off with, they're going to end up close by after the transformation. Okay. Yeah? So that's continuity. Okay. That's what we call continuity. The diffeomorphism is a bit even stronger. And it basically says that not only is this continuous, so it maps small sets to small sets, okay? We need to talk about differentiability, okay? So being continuous is, so being continuous is one thing, but actually there's this notion in math called being differentiable, okay? Okay. And that's actually nicer than being continuous, okay? Okay. So, let me draw you two curves real quick. We need to talk about what it means to be differentiable. If I draw you two curves in the plane, okay? So, okay, here's my first curve, okay? Okay. Here's my second curve. Okay. And there's my third curve. Okay?
Well, okay, the third one is...
The third one's crazy. Yeah. Basically, all I've done is for every real number here, yeah. X, I've given an output, f of x, which is the height. Okay. Okay? So for every point x, I've assigned it an output, a height. So this is like x, comma, f of x, where f is my function from the real line to itself, okay? Okay. So f is going to take every function of this real line mm-hmm. and give it an output, okay? Mm-hmm. That output is called f of x, which is another real number. If I look at the graph of these two numbers, the input and the output, mm-hmm. I basically look at the input as this horizontal axis, mm-hmm. the output as the vertical axis. So each of these curves are just an assignment of every point on here, I specify the height. Okay. Right? Yeah. So I can do this in a crazy erratic manner. in a manner that's so insane that I can't even draw it. Right? And this is just one example. The highest curve here is an example of something that's not even continuous, okay? So which curve do you think is the nicest of these? Which is the worst? How would you rank them in terms of how nice they are?
I think the last one you did is the worst.
Yeah, this one's the worst. Yes.
Nicest I would say it would be the second one. This one right here.
Yeah.
Would be the nicest and yeah.
So this one would probably be the easiest to understand, right?
Yeah.
Yeah, so this is actually what we call the smoothest, okay? And here, both of these curves are kind of more similar than this one, right?
Yeah, definitely, yes.
And that similarity is actually called continuity, okay? Continuity, continuous. And what does it mean mathematically? Well, let me just grab a different color here. What it means is that if I stay close, remember, if I stay close, so if I fix a point here,
yeah.
And now I look at a neighborhood of this point, so a small ball around that point, which in this case is just a small segment of the line.
Yeah.
So a small line segment here. And I look at where the function sends all of these points. Then the requirement of continuity is that they kind of stay nearby in the output, right? The outputs stay nearby the input.
Okay.
Do you see that? So this open ball gets mapped to this open ball here, or at least so this a set which is kind of in the neighborhood of the image point, right? I have my input here, here's my output height, and then if I change this input slightly, the outputs are going to change by a small amount, right?
Yes.
So this is continuity, and both of these two functions satisfy it, okay? All right, but then essentially the next level of continuous, okay, which is even stronger, is not only can I basically ensure that the values of the function stay nearby, I can actually understand how this interval is getting compressed, okay? So how much this interval is getting compressed. If I look at this, if I look at the original interval, and then I look at the interval that it maps to under the function, then this interval is either getting stretched or compressed by some factor.
Okay.
Right?
Yeah.
And the idea is to understand the factor, we can approximate the factor of stretching, local stretching, due to this map F, this assignment F here, this curve. We can do is actually assign what's called a tangent line or a slope. So a line that looks like this. Okay? And this line, this tangent line, approximates the function nearby this point. This is what's called the derivative, the slope of this line. So this is the tangent line. And the slope of this line is called the derivative of the function. But the idea is that this line somehow encodes the rate of change of this function, or how much this interval is getting stretched by the function. Okay, so in this case, the interval is getting squeezed, and the way that it's getting squeezed by a factor that is the derivative or the slope of this line.
Okay.
So if this line right now has a slope of like 1/2, right? Where it has basically a rise of a run. If I move over by 2, I move up by 1, right? So the slope of this line is like approximately 1/2. Would you agree with that?
Yeah.
And what that means is that the length of the input, so the input interval, its length is, the input interval is equal to the length of the output. Okay, so length of input interval is equal to the length of the output multiplied, where I multiply this quantity on the left by the slope of this line. So I have to multiply this by the slope, or what we call the derivative, which is 1/2, okay? So basically, if I multiply this length of this interval by 1/2, I get the length of the output. You see that?
Yeah.
And the line that approximates
Yeah.
this slope factor is what's called the derivative. So the derivative measures how much my function is stretching or squeezing the line. Right?
Yeah.
Does that make sense?
Yeah.
Okay, so if I have a derivative of like 5, then what that means is that at that point, locally, I'm stretching the line by a factor of 5.
Mm-hmm.
So you can think about taking a line, right? This is just the graph of a function, but, oh yeah, actually before we move on, let me just quickly mention that this construction here, right, that second line,
Mm-hmm.
which was like kind of friendly, but not super friendly, it is continuous, but notice that at these corners here, there's no way to understand what the tangent line is. There's no tangent line here.
Mm-hmm.
Because if I want to, I could try to approximate it with a line like this, but that's only going to get the left-hand side, and the right-hand side, I need to use a different line,
Mm-hmm.
right? So I can't, to these corners, this like sharp corner, I can't attach a tangent line like I can to a smooth function, right?
Yeah.
So smooth functions are, or differentiable functions, right? Smooth functions, you can repeat this process over and over again. Basically, you get a new function, like I can basically create a new function, which now, okay, starting with this function f, suppose that I start with this function f here,
Mm-hmm.
this is the graph of f, then I know that f has a derivative, and the derivative is the slope of this line at every point. So at every point, I find the line which touches the graph of f,
Mm-hmm.
and I get the slope of this line. Here's the slope of the line at this point, and maybe the slope of the line at this point is like this height, etc. So at each point, I get the slope of the tangent line, and then I get a new function whose output is that slope. That function is called the derivative. And I can keep doing this process as many times as I want if the function is smooth. But differentiable, I think that's a bit too complicated. We don't need the notion of smoothness, we just need the notion of differentiable. So again, all that means is that every point on this curve, since it's differentiable, I can attach a tangent line.
Okay.
And that tangent, the slope of that tangent line is called the derivative. Okay. Now, so we're almost there now because the C1 diffeomorphism. Okay. All that means is we have a function from Rn to itself. So let's draw it in R3. Remember, G is a function from omega into Rn,
Yeah.
where omega is a subset of Rn. But now we're just taking n to be 3. So again, we're going to kind of draw up one possible set here. Okay? And here's omega. Now the idea is that G is going to take omega into some other set. Okay? And what I can do is to understand this transformation. So here's G at what we call G of omega. So this is the set of points that get mapped by the mapping G. Okay?
Mm-hmm.
And to understand this transformation, let's look at what it does to a single point. Okay? So a single point can be described as x, y, z. Okay?
Mm-hmm.
And then a single point here can be described as by 3 coordinates as well.
Mm-hmm.
And we're going to call them G1, G2, G3, let's say.
Okay.
Yeah?
Yeah.
And G1 is actually a function which takes in x, y, z. So the input is this x, y, z here,
Mm-hmm.
and the output is the first coordinate of G. of the mapping of the function g. So this is what's called the first coordinate. Okay? And first coordinate function. And notice that this first coordinate function is actually a map from R3 into R. The output is a single number. The input is these three numbers, x, y, and z, but the output is just the first coordinate of the image point.
Yeah. Okay,
Makes
that
sense?
makes sense, yeah.
So each of these coordinate functions, we can understand how to take their derivative, okay? And by requiring that all of these coordinate functions are differentiable and that their derivatives are continuous, so the derivatives are the slopes of those tangent lines. Am I getting a little bit too lost here in the weeds? Or is this making sense?
It's still making sense.
Okay, it's still making sense. Okay. Yeah. So I basically want to require, to understand the mapping G, I want to focus in on these coordinate functions.
Yeah.
And make sure that those coordinate functions are in a sense smooth. Or mainly they just need to be differentiable. Okay? So we look at each of these coordinate functions and require that they're differentiable. Okay? But we haven't fully discussed differentiable from R3 to R. We just discussed differentiable from R to R. So the idea is that any map from R3 to R, let me just quickly specify this, and then we can take another intermission. We have our map G, we've taken its coordinate functions, right? Now, if I look at just a coordinate function, it's just going to output one real number, okay? So here is omega, and then G1 is going to send every point in omega to a real number, okay? Now here's the idea, is that if I take a line through this point, okay? So this point, first of all, this point contains a small sphere around it, right?
Yeah.
Because omega is open, right? Let's zoom into this sphere real quick, okay?
Yeah.
Let's zoom into the sphere. We're going to be doing this a lot. If I zoom into the sphere, okay, this sphere is contained in omega, and each point on the sphere, well, pairs of points on the sphere that are antipodal specify a unique line through the center of the sphere. Right?
Yeah.
You take a sphere, consider 2 points that are antipodal on the sphere, that specifies a unique line.
Okay.
Right? Now the idea is that G1 actually maps this line onto the real numbers, right? Because it maps the entire sphere. G1 maps the entire sphere onto the real numbers, so it better map this line onto the real numbers, right? But then, if I restrict G1 to this line, let's say L, I can say G1 restricted to L. I only look at L. This is a function from L into R, but L is just a piece of a line, right? L is just a line segment, right?
Yeah.
So I can view this really as secretly a map from R to R. And I know how to take its derivative, right? I know how to take its derivative,
Yeah.
right?
Yeah.
It's just the limiting of the secant line, right? Let's go, let me just recap here. So, and this is what's called the derivative of this is going to be the directional derivative in this direction, okay? But let me just say one last thing about the derivative, okay? So remember, we said that the derivative was essentially putting a tangent line onto a function, okay? So here, this is not a function, this is what's called the graph of a function, okay? You've seen graphs of functions before, right?
Yeah.
So here's the graph of a function in R2, where, right, I have an input x here, and then an output f of x, right?
Yeah.
Okay, and And of course, f is not this line. This is what's called the graph of f. F is a function from r to r,
Yeah.
right?
Yeah.
It's this mapping which assigns x to f of x, right?
Yes.
Now, this line here, we said it represents how much f locally stretches the line, right? I don't have to think about f as living in this plane.
Mm-hmm.
I can think about f as just taking a line and then stretching it, or translating and stretching it in some ways,
Okay.
right? And essentially x is going to get moved to f of x,
Mm-hmm.
and the area around it is going to get stretched or compressed. The area around it is going to get stretched or compressed by a factor of this slope, the slope of this line. Okay? So that's what we said before. But there's more to the story here. How do you actually calculate this line, right?
Yeah.
How do you find this tangent line? And the way you find the tangent line, do you have any ideas how you find the tangent line?
No.
Okay, what if I gave you a second point? How would you find a line? If I gave you 2 points, you could find a line through them, right?
Yeah.
Yeah, so if I gave you 2 points, let's say now x2 and f of x2, then you could find the line between these 2 points, right?
Yes.
So the idea behind the derivative is basically you take the line between these 2 points and then you make this point infinitely close to the other one. And when you make this point infinitely close to this point, then this line between these 2 points is going to approach the tangent line.
Oh God.
Yeah?
Yeah.
And then so that's how you find that tangent line, and the slope of that tangent line is exactly the value of the derivative. Okay? Right? The slope of that tangent line is the value of the derivative. Okay? So that's what we want to know. We want to know the slope of this tangent line. And that's rise over run, right? It's rise over run. Okay. And if we understand the slope of this tangent line, that's the derivative. It also encodes the local stretching factor. How much the map is stretching the real line. Okay. All right. So map G takes. Let's just draw an R3 here. It's going to take some subset of R3
And then I'll put it
into a different subset of R3.
Yes.
Right.
Yes.
And then we've said, okay, well, we're going to break this map down by looking at its coordinate functions, right?
Mm-hmm.
So its coordinate functions are, let's say, G1, which is the first coordinate of this point, G1, G2, etc. Okay? And this point is x1, etc. to xn. And so G1 is a function of all of x1 through xn here. So it takes in a point, but its output is just the first coordinate of the output of the function, right?
Yeah.
And so this simplifies, so now we can just look at these coordinate functions, and each of these functions are now mapping the real line. Here's G1. G1, the output is now just a real number, okay?
Mm-hmm.
So I'm mapping Rn into just the real numbers. Now I said that essentially I have this set here in Rn, and G1 is mapping to the real numbers, but how do we understand that in terms of its smoothness? Well, we want to keep in mind two things. The first is that, if I take a point, then I know that I'm going to have a sphere around that point, right? A small sphere around that point.
Yeah.
And that small sphere around this point is going to get mapped to some small interval centered around the image point, right?
Mm-hmm.
If this is my image, say the point now is here, then everything in this sphere is going to get mapped nearby. That's continuity, right? But we've required more. We've required differentiability, which means that if I look at this sphere and I zoom into the sphere, okay, then if I look at any line through this sphere, I can basically create a map from that line via G1 to the real numbers. I can understand this map from a line to a line, and I know how to take its derivative.
Yeah.
This requires that its derivative must exist no matter which line I choose. And that derivative is called the directional derivative of the function in this direction. Okay?
Okay.
And this is kind of crazy. It's basically a higher dimensional version of, right, the difference between this and this that we talked about before, right? This is like a higher dimensional version of that, where I'm requiring it to be smooth, the output to be smooth in every possible direction that I go.
Okay.
Here there's only one direction. I can only go, across the line.
Yeah.
Here there's a whole sphere of directions, but along each direction, I have this smoothness, this differentiability in each direction. Okay?
Okay.
Does that make sense?
Yeah.
Okay, so that's how we've broken down the function g. So g is now a function from omega to Rn, and it is C1 diffeomorphism. So what we've just described is just a differentiable map. C1 diffeomorphism is even a little bit better than what I just. So everything I just described is really nice, but actually this is even stronger. What diffeomorphism means is that it's what's called injective. So if we explain how the directional derivatives of the component functions exist in every direction, let me just write that down. So directional derivative of component functions exist in all directions at every point. Okay? So this is the first thing that I'm requiring for a C1 diffeomorphism. It's actually the most complicated thing that I'm requiring. So we got through the most complicated requirement. And does this sentence make sense to you after everything we explained?
Yeah.
Okay. So could you explain to me what the directional derivative is based on what I said?
The directional derivative, is that the line?
Yeah, that's the line through the sphere, right? So that we pick a point P, exactly. So we pick a point P, and this point is getting mapped onto the line via some coordinate function, G1.
Yeah.
And then the directional derivative, I choose a direction in the sphere,
Yeah.
and this reduces me to a map from this line to this line, which I then can take its derivative, right? So that's what's called the directional derivative, right? And this is the component function G1, G2, G3, etc. And they exist at all directions in every point. Does that
Makes sense.
make sense? Okay, great. So now that's the first thing we're requiring. The second thing we're requiring is that how do I explain this? Directional derivatives are never zero. Okay? So, what does this mean? Well,
It just means that it can't be a point, it has to be fully defined.
exactly. Yeah. That's pretty much right. So, that's right. So basically, if the directional derivative was zero, then
It'd be a point.
exactly. Then right. Then if we think about the graph here, then this is like the graph being flat somewhere,
Yeah.
and then this interval is actually going to get mapped to a single point. like what you said. So the interval is getting compressed too much. It's actually going from a positive volume to 0 volume. So we don't want that. We actually want that volume needs to be compressed but not actually destroyed by the map G. Okay.
Can it be reduced?
Yeah, it can be reduced. It can definitely be reduced.
Okay.
As we're gonna see, this theorem is really describing the way that the map G changes volume locally. Right? Just how this derivative stretches the interval and changes its length by the slope of the tangent line. This theorem is basically a higher dimensional version of how to figure out exactly how this map G stretches the volume of the space. Yeah?
Let's take an intermission.
Yeah, let's take an intermission.
That's crazy. Yeah, you did just teach me something. Way better than teachers.
Okay, well let me say one last thing before we take an intermission. Because this is the last thing that we're going to need to require. Or I'll just put a star here, where before we take the intermission, this is not all we're requiring for this to be a C1 diffeomorphism. There's actually one more stipulation. Yeah, one more requirement. So we're and we'll go over that after the intermission. But
what's the requirement?
The requirement is that that G must be injective.
Injective?
Yeah.
What do you mean
so,
injective?
Injective means it doesn't send two different points to the same point.
To the same point. Okay,
so
it has to all have different points.
Yeah, two different points are never going to get mapped to the same point. So if I picture like taking like a piece of Play-Doh and like bending it, I'm not allowed to like bend these two edges together. So I can't break the Play-Doh.
You can only stretch it.
Yeah, you can only stretch it and you can't make it overlap. So injective means that two different points never get sent to one point, okay?
Okay, that makes sense.
And in particular, these three requirements actually allow us to undo the action of G. So there's an inverse action, which is also a C1 diffeomorphism, so also satisfies these nice properties. Basically, you know how like fire, if you burn a piece of paper, it's an irreversible reaction. You can't undo it.
You can't undo it.
But the action of G is actually something that is nice enough that can be undone uniquely. Like we know exactly how to undo it. So these three properties are like requiring it to be nice enough where we understand how to undo the map, basically. If you put Play-Doh, say you took a piece of Play-Doh and you stretched the edge and then squished two of the edges onto each other so that it wasn't injective, right?
Yeah.
Then we wouldn't know how to undo that.
Yeah.
Right? Because if you take 2 points, think about taking 2 points and sending them onto a single point. If you want to go back, you don't know where to send this point.
Yeah. It'll just become one point, basically.
Yeah, it'll just become 1 point, so you can never send it back to the two. Right?
Yeah.
So this injective allows us to undo the action, basically.
Okay.
And these two other properties basically say that when we undo the action, we don't lose any information.
That's amazing.
Yeah. So that explains the first sentence, yeah?
Yeah. Perfect.
Okay. All right, so now let's take an intermission.
That was perfectly done. I can't lie.